we have center chord theorem. Center chord theorem. So center chord theorem says a line drawn from the center bisecting the chord. So we can see that AB is equals to BC. So this line cutted this AC into two equal parts. So whenever that happens, we know that OB becomes perpendicular to AC. And the reason being, it is center chord theorem. So again, they can give you that vice versa, right? They can also give you this as this line, and they say OB is perpendicular to AC. But you can see that this line is from the center and this is our chord. So if this is our chord and this is perpendicular to that, we can conclude that therefore our AB is equals to our BC. And the reason being, again, it is center chord theorem. So every time that they give you that you're having a center, so check if you're having a chord that is being bisected or the chord that is perpendicular to the what? To the line drawn from the center. So that is trick number one that you must always check. Whenever that they give you that you're having a center, right? And you're having a line drawn from the center going to a chord. So you must check for that. So let's go on to our other theorem. So now angle at center is equal to 2 times angle at circumference. So whenever you are having or you are given that there's an angle at the center and angle at the circumference, always check one thing. Are these two angles given by the same chord? Because you can see that we're having a chord AB. So if we follow the chord AB, it gives us our angle O1. And if we follow this, again AB, it gives us angle C. So we can now say angle at the center is equal to 2 times angle at the circumference. So it means that our O1 is equal to 2 times our angle C, like that, right? And most students often do a mistake of this. So let's just see. So we can be having our center here as O, right? And we can be having an angle like this, and you can also have maybe C there giving us the angle at the circumference like this. So this angle, this one, it will never be 2 times, it will never be half of this. There's no relationship between this angle and this angle because they're not given by the same chord. So chord AB gave us O, but now this angle, it is given by the chord CB. So that will never be the same. That will never be the case. And another common mistake that I've noticed in years is that we can have something like this and we can have something like this going on. So this angle will never be 2 times this angle because this angle is not at the circumference. So that will never work, right? So always check out for these two mistakes that I told you about just now, right? So that you can be able to locate exactly where this reasoning work, right? Yes. And now if we're having AB, C inside and AB as our diameter, now we can now say now our angle C now becomes 90 degrees. So this angle becomes 90 degrees because it was subtended by a diameter, right? So we can just say angle subtended by a diameter, or we can say angle in semicircle, like that. So this is one and the same thing, right? But we just have to know that this angle becomes 90 degrees. So now if we're having a situation like this, we can see that our chord AB or our chord AB is subtending angle C and angle D there. So we can quickly say our angle C is equal to our angle D, because these are angles in same segment, like that, or angles subtended by the same chord. The chord that we're talking about, it is AB. So if we follow AB, it will give us D there, and if you also follow AB, it will give us C there. So those are angles in the same segment and they should be equal. And again, don't make a mistake of if you're having maybe a situation like this. This angle will never be equal to this angle. This will never be the same. Why? Because this angle is subtended by another chord and this angle is subtended by the other chord. But now if we can have something like this, it means that this angle now can be equal to this angle because they're subtended by the same chord, right? Yes. And again, this reasoning gives also birth to this. Some people there don't know this, but let me just give you this for free. So inside the same circle, if you're having equal chords, so this chord is equal to this chord, they always subtend equal angles. So it means that our C again becomes equal to our D. And the reason being is because equal chords subtends equal angles. So equal chords will always subtend equal angles, just like that, right? So now let's move to a cyclic chord situation, right? So a cyclic chord is characterized by these things. So the first one we just talked about is angles in same segment. So if you can have angles in the same segment equal, that shape is a cyclic chord. Or if we are given that a cyclic chord, we can always say angles in the same segment, they are equal. And the other thing, it is this shape here. I'm sorry for the shape, guys. Maybe something like this. So this is our cyclic chord A, B, C, D. So we also know that opposite angles of a cyclic chord are supplementary. So it means that our B plus our D is equals to 180, right? Because opposite angles of cyclic chord are supplementary. We already talked what is supplementary, right? And also it will mean that our A plus our C, because this C is opposite to this A, so also equals to 180 degrees for the same reason, right? And also if we can extend a line outside here, so this angle is called the exterior angle of a cyclic chord. So angle D2 there, so this is 2 and this is 1, will be the same as our angle B. So this extended angle outside here, it will always be equal to the opposite interior, right? So we can just write that down as exterior angle of a cyclic chord is equal to the opposite interior angle. So the exterior angle will always be equal to the opposite interior angle. So these three things are the ones that makes a shape a cyclic chord, or if they are there, it means that the shape it is a cyclic chord. Or if a shape is a cyclic chord, then we know that we can look for these three things, right? So this is another trick. Whenever that they give you that this is a cyclic chord, always check for these three things. And again, if they say prove that this shape is a cyclic chord, then prove any of these three, right? Let's move. So let's talk about the tangent. So one thing that you must know is the tangent is always perpendicular to the radius or the diameter, right? So tangent is perpendicular to radius or diameter, right? So we can see that OB is perpendicular to AC, because tangent is perpendicular to the radius always, right? So that's one thing. If you're given that you're having a tangent, you check for this. And the other thing that you check for, it is this. This is a bit complex, but just check. Whenever that you're given that a line is a tangent, and you can see a triangle that is drawn from that point of contact inside the circle like this, just know that this angle here between the tangent and a chord, can you see that we're having a chord TA there? So this angle that is given here, it will always be equal to, if we follow that line, so we'll get this. So this angle will always be equal to this one, and this is the tan chord theorem. So that's the tan chord theorem. And also this angle that is here, if you can check, this angle is between this chord. Let me use a different color maybe. If you are having this situation here, so this chord BT, it is making up this angle. So we just follow the lines BT to see where they are going, and they are going here at here. So it always mean that this angle is equal to that angle on tan chord theorem. So that's tan chord theorem. So the last one that we can have on tangents, so this is the second situation that you have to check for whenever you are given tangents. We can also have, if we are having two tangents from the same point outside the circle. So these two tangents from the same point outside the circle, they will always be equal from the point of contact. So like this, so this will always be equal to that. So always check for this as well when you are given two tangents, right, at the same circle. So we can say tangents from same point outside the circle are equal, right? So it means that our AE will be equals to our TE, because tangents from the same point outside the circle are always equal, right? So now that we are done with the whole summary of Euclidean geometry up to so far, I'll just give out some questions so that we can try to work on this, right? So we just take it a step at a time, no rush. And then just because of the length of the video, I'll just do another one focusing on the grade 12 work. But when it comes to grade 12 work, I'll just put in the details a bit so that it sinks in, right? I wish you guys good luck. But before I can go, obviously, let's solve some questions.